What's up, geometry? Thanks for tuning in for another episode of Math with Mullins. Today we're going to look at lesson 4.3, rotations. So how can we perform rotations and compositions with rotations, and then how can you identify something called rotational symmetry? The first thing we're going to talk about are three word terms here in vocabulary. First off is we want to know a rotation is a transformation in which a figure is turned about a fixed point. The center of a rotation is where that point, the figure, is being turned around. And then the angle of rotation is how much a figure is rotated and its direction. So we'll talk about clockwise versus counterclockwise, and we'll also discuss like our main degrees of rotation being 90, 180, and 270. Take time now to pause the video here to make sure you've gotten your definitions filled in. And when you're ready to go on, let's click play. All right, the coordinate rules for rotations about the origin. So this is going to be our big help to understand where these things go, because for a lot of us, rotations can be challenging, especially because reflections in translations, as we've discussed before, are very easy to transform, but rotations are a little bit trickier. We want to make sure we understand that these are also showing counterclockwise rotations. So if we counterclockwise 90 degrees, my points would just switch their places and the y would become a negative. A counterclockwise 90 rotation is also a 270 clockwise rotation. Okay. For 180 degrees, both x and y coordinates are just going to change to their opposites. So if they're positive, they're going to change to negative. If they're negative, they'll change to positive. 180 degrees counterclockwise is also the same thing as counterclockwise. So both of these would work for both. But 270 degrees counterclockwise, you're going to switch B and A, but A would just become a negative. This would also be the same thing as a 90-degree clockwise rotation. Okay, so those are the things we want to pay attention to. We're going to use these all throughout, but make sure you also understand that 90 degrees counterclockwise is 270 clockwise, and 270 counterclockwise can be 90 degrees clockwise. Continuing on, we're going to try this example, and what I would recommend is understanding your rule first. So we're going to write rule, then graph. Okay, it says the graph of the quadrilateral RSTU with vertices of 3, 1, 5, 1, 5, negative 3, and 2, negative 1, and then its image after a 270-degree rotation about the origin. And we're just going to assume that this 270-degree rotation is the one that was discussed here. The B and A are switching places where A is becoming negative. The first thing we want to do is just graph our original points. Let's go ahead and take time now to do that. You can go ahead and pause the video and try that on your own. And when you're done, click play to see what happens next. All right, so what we've got here is looking like RST and U. It looks kind of like a kite. Now we're ready to rotate it about the origin. Remember our rule from here, 270 is B comma negative A. So that means we're going to switch the placement of X and Y and just make X turn to its opposite. So R prime, we're going to go and switch 3 and 1 and make it 1 comma 3, and then 3 would now become negative. S prime, we're going to switch those places, 1 and 5, where 5 becomes negative. T prime, switch the placements of negative 3 and 5, except 5 would also become negative here. And then U prime, switching the places of 2 and negative 1, so I'd have negative 1 comma 2, except 2 would also become negative. Now let's go ahead and plot these points. Here's the final result of our rotated figure, R prime, S prime, T prime, and U prime, all of those points being plotted around the origin using 270-degree rotation. The next thing we want to understand is the postulate that supports this. The rotation postulate just says a rotation is a rigid motion, which means it does not change the size or shape of the figure. Now we're going to go on and talk about how can we do a combination of those rotations and reflections. It says graph RS with endpoints R being at 1, -3 and S2, -6, and its image after the composition. So the first thing we want to do is plot R as 1, -3 and S2, I'm going to scroll down here, -6. Okay. What we're going to do next is we are going to connect this because this is now a line segment, and it says to reflect it across the y-axis first and then 90 degrees about the origin. So let's go ahead and do that reflection first. I'm going to do that in green. Reflection across the y-axis. R is only one jump away from the y-axis, so R prime would be one jump away. S is 1, 2 jumps away, so 1, 2 jumps away for S prime. What we want to look at now is R prime is now at -1, -3, and S prime is now at -2, -6. We are going to go 90 degrees about the origin. So if you remember back from our rules, 90 degrees about the origin is -b, a. So -b, a means we're going to switch the placements of x and y, and x will now become its opposite. So our double prime is now going to look like this. -3 is out in front, but it's actually going to be its opposite. So that -3 is going to change to a +3. All right, so we have all of these. I'm just going to go mark these. These are going to be our opposites, and the other ones will switch. So -1 is still okay. And then S double prime, the -6 will switch to its opposite to be a +6, whereas -2 will go in its place and just remain the same. So that's a little bit easier now because now we see it's easier to see where those points should go and how to graph them. 3, -1 is going to represent our R double prime, and 6, -2 represents S double prime. So there's our 90-degree rotation about the origin. The last little bit we're going to talk about is rotational symmetry, and that is when a figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. The center of symmetry is where that point is used for rotational symmetry. So we're going to look at a few examples of what could have possible rotational symmetry. Do the following figures have rotational symmetry, and if so, describe any rotations that the map could figure onto itself. Maybe pause this one and see if you can think about which ones do. What rotations could they use? What degree measurements maybe? And then when you're ready to check, click play. All right, so this first one, what I like to do is I like to also draw line from vertices to vertices because this also helps me kind of picture what my rotations could look like, and then a point here in the middle. What I notice is that I can rotate this 180 degrees and it'll show rotational symmetry, meaning it'll appear to be the same shape, and I wouldn't have known if it would have rotated. Regular octagon, again, what I do is I take vertice to opposite vertice and I just continue that throughout the entire thing, and this really kind of helps to see how many times I could rotate it. Here in the middle, that's my center of rotation or center of symmetry. And if you notice, each one of these lengths is the same. So I could do a short rotation, a much bigger rotation, and so forth. So I'm rotating around to each kind of from one vertex to the other where it could still be the same. So some of you probably said 180 degrees. That's a good one. You could also rotate 90 degrees, but you also should be able to see if you look maybe like this. This is a 90-degree angle. Sorry for the interruption. This looks like a right angle right here. And you notice it's being separated by this pink line here. That is also going to show a 45-degree rotation. So because you can rotate every 45 degrees, you can also rotate 90 degrees plus 45, which would give you a 135-degree rotation. So all of these could be rotation points. Okay. So we can rotate at 180, 135, 90, and then 45 degrees. One way you can also think about this is a full circle is 360 degrees, and we have 8 sides. So when you divide 360 by 8, you're going to get 45, and that's each rotation of degree measurements. Okay, and that just works with regular figures. The next one we see is a trapezoid. And again, if you want to do opposite vertex to opposite vertex, but notice how the center of symmetry is a little bit off. So there is no rotational symmetry, because what I would have to do in order for it to be the same thing is I would have to rotate it a full 360. So this is no rotational symmetry, because you would have to rotate 360. And remember, rotational symmetry has to be less than 180 degrees. Less than or equal to 180 degrees. Okay? So that will conclude our notes today on rotational symmetry and rotations. That hopefully helped you just a little bit understand how to rotate. Make sure you're using those rules on your homework assignment. If this video helped you at all, give it a thumbs up and subscribe for more videos to help you